Now let's look at some examples of coupled acoustics problems. The first is going to be an automotive case with a vibrating engine that's giving sound that passes through the dash panel and into the passenger compartment. The second is going to be an airplane where the external engines mounted on the wings will excite the cabin itself and then transmit noise to the interior. The coupled acoustic problem that we'll show for the automobile is that of an engine vibrating under the hood and then noise being transmitted into the passenger compartment through a flexible dash panel. Here we see the mesh of the outer surface of the automobile, and typically this surface shown here is going to be taken as rigid in this simplified problem, and the flexible surface that couples the two acoustic regions will be the so-called firewall or dash panel that's between the two compartments about in this region. We'll now look at the interior of the automobile. Here we see the engine model, which is simplified as a rectangular prism. This will be an active noise generator through surface velocities on the engine. Then you see the dash panel as a rectangular panel here, which will be considered as elastic and the transmitter of sound from the engine to the passenger compartment. Then the sidewall of the vehicle shown here on the far side, the interior, which primarily is in the form of these seats and the floor. Now, these are all going to be considered rigid surfaces for the purpose of this study. So we're basically looking at a simplified automobile where the engine makes noise, passes through the dash panel, and then impinges on the people sitting in the passenger compartment. But the outer structure is considered rigid, and this seat area is considered rigid. The passenger compartment and the engine compartment have been fairly well modeled to show the cavity effects, so the length scales are properly done. The elastic panel between the two cavities is studied in some detail as well by using MSC Nastran, and that is done on a modal basis so that we characterize that flexibility by the normal modes that can exist in that coupling panel. Now, one thing that happens is that in the indirect boundary element model, when there are free edges, or in other words cut edges, as on the forward part of the engine compartment down at the base of the model there are free edges of plate elements, and those are required to have a constraint applied. Likewise, there are some multiple connection places, particularly around the dash panel itself where it connects with the sidewalls, for instance. And that's where you have more than two plate elements coming together, and there needs to be a continuity in the pressure as it's measured as pressure jumps. And that's all handled automatically as a multiple connection constraint. We're going to use a unit velocity on the engine surface to create the noise, and it's in phase over the surface. So it's as if the engine were pulsating with that amount of area being effective in pumping noise out to the surrounding field. This modal basis for the elastic dash panel characterizes the different ways that the panel can vibrate. And it then is a transmitter of energy from the engine compartment to the passenger compartment. When you put that in, then you are actually including the boundary conditions that are present around the rim of the dash panel, and then that allows you to characterize that transmissibility in a thorough way. Now, when we solve the problem here, we have to do it in the following. I'm going to outline about 16 steps. First of all, you do the acoustic finite element model and the data recovery mesh. these are rather geometric situations, and so we use the MSC Patran code in this case. That is output into a neutral file format in Patran terminology. The dash panel analysis was done in MSC Nastran and resulted in a set of normal modes. We'll assume that those two steps just outlined have already been completed, and we won't go into a lot of detail on that. That's a little bit in the spirit of the example manual for Comet Acoustics, where there are certain fundamental steps like the normal modes and the basic setting up of the geometry that are assumed to be understood fairly well. Now, the following steps are going to be done within the Comet Vision program. So we import the acoustic model, which includes the engine, the automobile, the dash panel, into Comet Vision. Then we have to check which of those edges of the sheet metal are free edges, and those have to be properly constrained, because in acoustics that's a bit of a untamed situation where we need to set some pressure jumps to be zero. Also, the multiple connection situation, for instance, around the dash panel, there are cases where you have three different sheets of material coming together, and again you need a continuity condition to make sure that you don't have pressure jumps that are unrealizable. So these are all tamed, and that's automated within Comet Vision. But I'll show you the figures where we call out the relevant nodes in a minute. As always, you define and save the views that you'd like to have of your model. You create groups for velocity boundary conditions, which would be the engine in our case, and the modal basis application, which would be on the dash panel. Then we apply the unit velocity conditions for the engine, which is an idealization. We're assuming that the engine's pulsing in and out with the same phase relation over the entire surface. We assign the material properties to the air, which are sea level in this case. Then we set the important analysis parameters, such as the frequency desired. We write out a Comet Acoustics data deck and save the database. Now that's part of the story, and then the other part is the modes that are in the dash panel model. So those are imported now into Comet Vision. Now we'll finish the process for our coupled solution. Number 12 here has to do with handling the modal results in a punch file. We write out the Comet Acoustics data file for the modal basis. That's going to be the dash panel information. And then within Comet Vision, you can merge the original Comet Acoustics data, which is always required in acoustics programs, with that from the modal basis that gives you the coupled motion here. Then you exit the Comet Vision program, and then you come into Comet Acoustics and run your basic acoustics solution. Then you return to Comet Vision and post-process. Now let me show you some more of the geometrical ideas involved in setting this problem up. The dash panel is this rectangular panel with the rectangular mesh, and it's the one that the modal analysis was done within MSC Nastran. Then here you have the need for free edge constraints shown as red nodes around the cut edge of the lower part of the engine compartment. Those are just flapping in air, so to speak, and that sharp edge is a problem in acoustics that needs to be tamed. You can see the dash panel itself is sitting in this region here. It has its own set of problems as multiple junction constraints are needed. I'll show that in the next figure. Now I'll point out the nodes that are important for this intersection constraint. They're pointed out in blue on this figure, and they're a problem along the top of the dash panel and down the sides of the dash panel. That's where you have 3 different pieces of sheet metal that have been welded together, and then you need to have a continuity condition on the pressure jump. That's all handled automatically within Comet Vision, so it's been automated, but the user has to call out those nodes. When you put the entire acoustic model together, you get this oblique view which shows the engine, the dash panel, the outer shell, the seats. So this is our completed acoustic model. Now let's introduce the noise source to our system. That's the vibrating engine. We'll create a group that will be the engine surface, and then we will impose the velocities on that surface. Here, in creating the group, we've highlighted the engine elements in red as shown. And then when you impose a unit velocity on that and then illustrate that in Comet Vision, you get the figure below. These vectors then illustrate a motion, a pulsing motion of the engine where all the surfaces are in phase. The sound pressure levels inside the passenger compartment are interesting. They're important to the passenger, to the driver. We're going to look at those on vertical viewing planes that pass through the center line of the driver and the right-hand passenger. The excitation was at 70 Hertz, and that corresponds roughly to the first longitudinal mode of vibration in the passenger compartment. As it's shown, it's a half wave extending from the front of the compartment to the rear. The decibel readings that we show here reach some 70 decibels, so it's a little bit noisy, and but it was just an artificially contrived engine excitation. The sign sense here is obscured a bit by the decibel reading. Namely, with the snapshot in time, if the dash panel here were vibrating to give a positive high pressure in the front, then you would have a zero crossing near the passenger's head for this mode, and then a negative pressure at the back of the vehicle. And so this really is a half wave. Maybe from front to rear along there I should just sketch that what you might have is a wave like this. And we've seen earlier that that's the longest wavelength possible in a closed cavity. So we've pretty well excited the dominant vibrational mode within the passenger compartment here. It's fortunate for this particular frequency that the passengers whose heads are in this region don't hear very much, and so it shows that life has its benefits after all. I was asked by one of the viewers of my linear static finite element analysis course as to why I didn't tell jokes like I used to in the old days on my video training. And I realized I stopped doing that, so I'll have to tell a story right now. It's kind of a cute story I heard yesterday. There was this mushroom that went into a bar, and the mushroom says, "I'll have a drink, and give me a whiskey and soda." And the bartender said, "Why, yes, sir." And then the mushroom looked around and saw a lovely lady down at the end of the bar and says, and give her a drink too. And so he said, "Okay," and went down and gave her a drink, and she kind of giggled and waved at the mushroom. So after a while, the mushroom finished that drink and went on for a second and told the bartender, "Ask her what she's having and let her have another drink on me." And so the bartender did, and the woman at the end waved again. So when the mushroom was done with his second drink, he strolled down to the woman and said, "Say," he says, "how about you and me getting together and stopping over at my apartment afterwards? We can stop and have some drink, watch some TV." And the woman said, "No, I'm sorry, I just couldn't do that." And the mushroom says, well, why not? I'm a real fun guy." So now, while you're while you're moaning and groaning, we'll go on to our second example here, which is an airplane example. And here we have an airplane cabin that's got two engines outside that are creating a lot of noise. And the question is, how much of that noise travels from the engine through the air and then into the cabin proper? This was particularly of interest in a few years ago when people were very worried about the noise generated by the large fan engines that were being proposed. This was a way to get a larger amount of air at lower speed through a large propeller turbine combination, but it made a lot of noise. So here is the cabin layout, and then here are the engines externally. These could as well be jet engines, of course, pure turbojets. We're going to look at the excitation transmitted into the cabin at 70 Hertz. Let's discuss the modeling involved in this problem. I'll start with the physical modeling and then progress to boundary element modeling. On the physical side, we're going to make the passenger compartment be a closed structure so that there is no direct acoustic path through the air from the engine to the people inside. The enclosure will be elastic and will be characterized by normal modes. The engine noise is going to be represented as point sources located in the proper positions on the wings. Now, the boundary element modeling, well, we created the mesh in the program ideas and developed the elements and their connectivities and output that as a universal file. The modal analysis of the fuselage was done with MSC Nastran, and that gave us our basis for coupling then between the internal air cavity and the external air. I'll describe the solution procedure for our coupled aircraft problem as a 17-step procedure. The first two steps are presumed to have been done already, and we won't dwell on those. Those were the development of the boundary element mesh within ideas, and then the modal analysis within MSC Nastran. Now, our example is starting here, and this is also documented rather thoroughly in the Comet Acoustics Examples Manual. You import the acoustic model into Comet Vision, and then many of the following steps are within Comet Vision. You define whatever views you'd like and save those. You create groups for your acoustic mesh. You define a data recovery mesh. That's going to be an interior set of surfaces. The following steps are still done within Comet Vision. You create your group for the data recovery mesh. You add these point sources for the engine noise. Assign material properties for the air. Again, describe frequencies and some other physical data. We're using 70 Hertz again on this problem. Write out your Comet Acoustics data set. Then you need to import the Nastran model of the structure in the form of the modal basis and pick out the proper modes that you're interested in. You then write out a Comet Acoustics data file containing this modal basis. You merge the acoustics data and the modal basis data. This is done within Comet Vision. Then you exit Comet Vision and go into Comet Acoustics where the actual solution run is made. Then you exit Comet Acoustics and go back into Comet Vision and post-process. We need to see some of the graphics that show what was done in those previous solution steps. So now we'll back up and show you what figures are available. For instance, the fuselage model that was imported from SDRC Ideas is shown here. Rather simplified. It's a cylindrical body with end caps, you might call bulkheads, shown in the front view here. Then in the side view you see it's a relatively simple view, very repetitive structure. This might in fact then represent, say, a portion of a passenger compartment within the fuselage. Next we'll look at an isometric view of the same fuselage. Here that is, and within Comet Vision you can look at the elements in the acoustic mesh and make sure that they've been properly formed and connected. The viewing planes that have been chosen run both in the longitudinal and the lateral directions. Here is the data recovery mesh up above. There are some stations which are basically like bulkheads extending across the cabin, and then there are two larger, longer planes that run along the length of the cabin, here and here. You can identify the element numbers to check that out as well. Now we'll show where those interior viewing planes fit into the total fuselage. Here's where the lateral planes, these bulkhead-like planes, occur spaced down the fuselage, and then the longitudinal planes are shown in this figure along with the lateral. So those are the regions that we're going to be able to find sound pressure levels upon. Now we'll show the figures where the engine noise sources are added. First, here's the one here on the right side, and then here's the one on the left side. So at least that orients the noise sources. The acoustic medium is air and at standard sea level, so we choose these values. Speed of sound at 343 meters per second, density 1.21 kilograms per meter cubed, and here's our reference acoustic pressure of 20 micropascals. The structural interface in this problem is the entire fuselage, and that's viewed as an elastic interface. So it forms the boundary between the outside acoustic medium and the inner acoustic medium. Our final figure shows the sound pressure levels within the airplane fuselage. If you were an aircraft designer, you'd want to make that situation as comfortable as possible for the passengers. It appears that at our 70 Hertz excitation that we're exciting a longitudinal wave, almost a one-dimensional wave. It's a standing wave in the fuselage. From the zero crossings that are the green areas, you can tell that there are 3 or possibly 3.5 full waves in the fuselage. So this isn't the lowest frequency possible, but would be one that at this frequency would be a problem for anybody sitting in those higher pressured seats, more noisy seats. Since the actual noise, though, is a combination of many frequencies, you shouldn't get too carried away with what are quiet and noisy seats in this airplane just on the basis of one frequency. Obviously, if that were a dominant frequency in the case of a propeller-driven aircraft, let's say, then that would be your dominant interest. But I think in general there are many noise sources, and some judgment has to be used as to the psychoacoustics as well in this problem. Well, I think you can see from these coupled examples that there are a lot of possibilities now to look at products and try to fine-tune their acoustic behavior. And I think the customers in the world are going to be more and more demanding, particularly in respect to unwanted noise.